Hey guys, I'm Shiki and I would like to welcome you to today's episode. As some of you may know and others may just find out, on this channel there's an ongoing series called Path to DevOps. My aim through this series is to show you a bit of what it means to be a DevOps engineer, and if you're planning to start this career, help you out a bit by having a demo application take its path through the whole software development lifecycle plus DevOps cycle. It's pretty hands-on, so don't miss out on it. Well, in order to move on to the next step, because in this series so far we've just installed everything locally and tried to understand the applications a little bit, we need to understand containers. And this buzzword has been going on for years, and what I want to do in today's video is just give you this crash course on what containers mean and how you can interact with them and understand them. So you can watch this video standalone, but if what I said earlier sounds interesting and you want to learn more about DevOps, check out my other videos. So without further ado, let's jump right into business. Let's get this containers crash course started stat. The first thing on today's agenda is the agenda. And we're going to touch up on three things: what containers are, how they work, and how to create one. We're trying to keep things simple because containers are a vast subject, and I'm just trying to give you enough tools to understand what a container is and be able to operate one without actually going into the nitty-gritty of things. However, if you like my way of teaching and you want to understand more on this topic or other topics, just leave a comment down below and maybe I'll make it happen. For us to better understand containers, we need to take a sneak peek inside of them. And usually what you'll find inside of a container is a main process. And in our example, our main process is going to be our application, our web application. And this web application has dependencies. Now, together, we'll call them software. In order for software to function, it needs to consume hardware. And we have here memory, CPU, and storage. Now, this can't happen out of thin air. Software can just consume hardware. It needs an intermediary. And in our day-to-day example, on our laptop or on our today's gaming rig, let's say, we have an operating system as the intermediary. Yeah, so you have hardware components, an operating system, and then you run applications on top of that operating system. That's the simplified version of the reality. However, if you wanted to install a production-grade application, you would need more than your host from home. You would need a solution that's more scalable and automation prone. And that's where virtual machines come into play. Hardware virtualization relies on a hypervisor, which is the gray box on the screen. This gray box will consume the hardware and then create virtual pools of hardware that can be fractionalized or split between the operating systems sitting on top of it. So we have virtual machines on top of the hypervisor. And that Windows virtual machine that I just made appear on the screen is using the memory, CPU, and storage that are virtualized by the hypervisor. And so is the Linux virtual machine and the Mac virtual machine, because the fun fact is you can have different OSs on the same hypervisor. And yeah, the application and dependencies will run on top of them just like before. Now that we've talked about physical hosts and virtual machines, let's jump to today's pièce de résistance, containers, because that's what we're here to talk about. Containers need a pre-existing operating system, and every operating system, be it Linux or Windows or Mac or whatever, they all have a kernel. The kernel is the core of the operating system. It's basically the component that takes care of memory access and talking to the processor. On the operating system, we will install something called the container engine. And using this container engine, all of the containers that will live on top of it will be able to access the operating system's kernel. By doing this, containers are able to be much more lightweight because you no longer require to run a full operating system for each application. You have your host's operating system, and you're just using its kernel, and then you're adding your dependencies next to that kernel and the application, and you obtain something that's a lot more lightweight than a virtual machine. And because the operating system is Linux in this diagram, we can have an Ubuntu container or a Red Hat container, or we could have an Alpine container or any other Linux distribution type of container. But we could never have a Windows container on top of a Linux operating system, or vice versa, a Linux container on top of a Windows host operating system. And then inside of the container, obviously, we have the application and the dependencies. Let us now compare hosts, virtual machines, and containers, first in terms of setup. And in the left corner, hosts are actually pretty manual. You need to put that hardware together, install the OS, and then maybe you can script the part where you install the application and its dependencies. With virtual machines, we're actually better off because you can create a virtual machine image and then use that image to instantiate multiple identical virtual machines. But virtual machines tend to be quite heavyweight because they contain a full operating system, so they can actually weigh few gigabytes. While containers are the most automatic because you also have images and they're pretty lightweight in terms of hundreds of megabytes, even if not tens of megabytes. It takes virtual seconds to spin up a container and have it running. In terms of resource usage, our third place goes to hosts, again, because they're not quite optimized. Once you have allocated the hardware to a host, you can't do much about it. And if your application on the host consumes only 20% of that, you have 80% that's sitting idle. In terms of virtual machines, you can actually scale on the hypervisor. You can tell it how much to allocate to a virtual machine. And if you take the virtual machine down, you can scale those resources up or down. But again, if the application inside of the virtual machine isn't consuming as much as you want it to, and it's basically 60% idle or 80% idle, those are resources that you're losing with your virtual machine. While for containers, they are the most optimized because sitting on your operating system and running lightweight applications, you can actually set them up to consume either as much as they want, or you can set them from the command line to have resource limits in order of usability. But the caveat here is you can also run multiple containers in parallel on the same host, and they wouldn't even know that they sit next to one another and that they're using the same host's resources. It's pretty cool. Finally, in terms of creation time, we have the absolute loser, hosts, which take hours, if not days, to be spun up and configured. Then, on the second place, we have virtual machines, which take tens of minutes, maybe hours, to be brought up. And that depends on the level of automation you put in. And then we have containers, which are the fastest. It usually takes tens of seconds or maybe minutes to download a container image, run it, and have the process inside of it start and be up and running. To be fair, I did not create this comparison in order to be able to say, yeah, containers are the best. Thanks for coming to my TED Talk. I don't consider that to be true. What I consider to be true is containers and virtual machines are two different solutions to the same problem. It just depends on your parameters. If you have a lightweight application, choose containers. If you have a heavyweight one, go with virtual machines. If you have one process, go with containers. If you have multiple processes that need to run tightly coupled together, choose a virtual machine. If you don't care about your process dying multiple times and being restarted, then choose containers. If you want to take care of your application, keep it up and love it, then choose virtual machines. And I chose these two keywords, cattle versus pets, because this is a nice philosophy. You can read about it more online. Once again, containers and virtual machines have the same purpose: running applications inside of them. They achieve this in different ways, and they might be designed for different types of applications altogether, but they are not competing solutions. In my opinion, I think they're actually complementary to one another. Having talked about containers, architectural design, and characteristics compared to VMs, let's see how they work now. As mentioned previously, you could run multiple containers, one next to the other on the same host. And if you are inside one of those containers, you won't even know the others exist. So how do we achieve this degree of separation between them? Well, it's pretty simple. We rely on some Linux technologies, mainly namespaces, control groups or CGroups, and ChangeRoot or CHroot. In the next sections, we're going to do a follow-along type of exercise where we demonstrate each of these Linux technologies. In order to follow along, you can check out my GitHub account linked in the description down below, where I have this markdown that guides you through the whole process. Without further ado, let's jump into the first one, which is namespaces. And this one has a keyword in light blue, isolate. So the task of a namespace is to isolate what's inside of that namespace from the host. Let's see how that's done. First, I would like to mention that we're working inside of a Ubuntu 18.04.3 LTS, which you can also get on your Windows machine by running it inside of Hyper-V. And you can follow the article in my Markdown document here at step 0, initial setup, in order to get it up and running like I did here and follow along. So to test namespaces, we have the theory right here, and let's jump right through the practice part where we want to follow along. And I have two terminals because that's what it says here, open two terminals and follow along. So let's do that, and we're going to run ps-ef. This basically shows us the processes that are running on our host, right? And as you can see in both terminals, it's a lot of them, right? And it's the same list, or at least it should be the same list. But again, a lot of processes. Keep that in mind, yeah? And what we want to demonstrate here with namespaces is that we're going to get a lot less processes in one of the terminals. And that would be terminal 1, because we're going to use the unshare command, which will basically, as you can see here, we will isolate inside a new namespace our processes. And my user also changed from Shiki, which is a normal user, to root, yeah, the root user of the Ubuntu VM. And now if we test the process command again, in here we will see the same result, which is a lot of processes. And in the first terminal, let me copy it again, we should see a different result. And voila, we only have two processes running in this namespace. The first one is the actual bash terminal, which we've opened as root, and the second one is actual the ps command, which showed us the processes. So what this tells us is that from outside of the namespace, which is basically the second terminal, the one at the bottom, we can see the namespace being created, and it's a process with process ID 4503. We can also see the bash, we can also see the process command being run, but from inside the namespace, everything else doesn't appear. So that's how containers do their magic and actually isolate what's inside from what's outside on the host. Moving on to the next topic, we're going to talk about CGroups, and the keyword for CGroups is limit. That's their purpose, and it means they take care of the resources that the processes inside of the container consume or are allowed to consume. Let's jump to the demo. Same setup as before. We're going to use the markdown on GitHub to show us around. So we also need two terminals for CGroups, and in the first one, let's elevate our permissions and switch to the root user. And I need to type in my password. Yep, here we are. Now I'm the root user on terminal 1. And let's create a new folder inside of the CGroup memory subfolder. Yeah, so I'm creating a memory CGroup effectively, and the memory CGroup will be called Shiki. Yeah, as you can see here. So now I'm going to set a limit. Okay, that's done. And now let's create a test script. Make it executable. Now this test script will only print something to the screen and then go to sleep. As you can see from the code, it's nothing suspicious. And we're going to run it and also see its process ID. So this is the process ID of our script, and we'll need it in just a few moments. Now on the second terminal, we want to assign this process to our C group, and let me elevate my permissions here as well. All right, I am root now. Let's put this in here and switch the script process ID with the actual process ID, which is 4611. And it's done. And now let's output this. And again, the process ID. All right. And as you can see here, the memory is from group Shiki. Yeah. So now if I was to run an extensive application, it would actually get throttled to this amount right here, which is, I think it's 30 megabytes or around 30 megabytes memory. Pretty low. Yeah. And if you want to clean up, you can follow the information here, but I'm going to do that off screen. Having seen how we can use C groups in order to limit the resource consumption inside of a container, let's jump on to the next topic, which is CHroot. And the keyword for CHroot is confine, because you can use CHroot to actually send applications and processes to jail inside of a folder structure. And basically they can't see any other folders outside of that structure. Let's jump to the demo. For this demo, we need only one terminal and our faithful markdown file, which tells us what to do. And as the exercise goes, we will copy the bash executable inside of the jailed folder that we will create in order to see how much of the file structure can bash actually get access to. First things first, I need to elevate my permissions, and I don't actually need to do that for all of the commands, but I will do it for simplicity's sake because I don't want to write sudo in front of everything. And I will create a jail folder. Now, we will run this command in order to see the dependencies for bash to run, because bash isn't just a binary that you need to copy, it also has some dependencies in the libraries. And lo and behold, inside the lib folders, we have these dependencies, and I'm trying to make things shorter for you guys to understand. So I'm just going to copy all of those folders inside of my jail, right? So here we go. This is it. The commands are here. Yeah, you can follow along, and everything has been done. So now I'm just copying the bash executable inside of the jail folder. And let's test it, shall we? And I've opened a bash terminal, as you can see here. Now let's do a list in the root. There we go. We can only see the folders that we've copied. Yeah, we've copied the bin, the lib, and the lib64 folders. But if I was to open a new terminal, yeah, on my operating system, and I would do the same command, list in my root, there we go. We have a lot of folders and files. Yeah, so because I jailed the bash process, it can only see as much as I allow it to see. And that's how containers achieve that layer of confinement. Time for a recap. In order for all of these new terms to stick, we have three things that we discussed about that help a container achieve its degree of isolation from the host. The first one is what separates the processes inside of the container from the host, and that's the namespace. Then what limits the consumption of the processes inside of the container, and that's CGroups. And then what constrains the file structure that gets accessed by the processes inside of the container, and that's Chroot. Obviously, these are not the only three technologies that are used by a container, but for simplicity's sake, I just presented these three as I find them most important. We have now reached our final checkpoint in this saga, and that is how to create a Docker container. For full transparency, I'm not using Docker Desktop because I don't want to bother with the licensing model, and I'm actually using Rancher Desktop, which by clicking in the settings menu, Docker CLI kind of achieves the same thing. And I'm encouraging you to do the same thing if you don't want to bother with the licensing model on Windows for Docker Desktop. I'm going to leave that linked in the description below. Without further ado, let's talk containers. In order to create a container, you need to go through a certain life cycle. And when I say create a container, I mean actually author your own container, because it's easier if you download a pre-existing image and you run it yourself. But if you want your own container from scratch to contain your own application, you will need to write a Docker file, which is basically a set of human readable instructions that the Docker engine can interpret, and the output of the Docker file will be an image. Once you have the image, that's actually your exchange coin, let's say. You can move that around, you can put it in a remote registry, you can share it with other people, and if you run the image, that's when you actually obtain what we call a container. So, very important thing, don't confuse these terms with one another, okay? And in order to help you, I'm going to give you an analogy to make things simpler. Yep, you're reading that right. It's an analogy about cookies, because who doesn't like cookies, right? The first thing is the Docker file, and you can think about it like a recipe for cookies. You have the list of ingredients in there, and basically if you follow it, you will obtain a dough. And that dough, in our analogy, is going to be the image. Is something that you can refrigerate, move around, share with your friends, but basically it's not the final product yet. And still, it's not the recipe either. It's the result of the recipe. And then moving on to our containers, which are the cookies, basically from the same dough, by adding different toppings and slightly changing the ingredients at the end, you can have chocolate chip cookies or oatmeal cookies or raisin cookies. And in the end, that's exactly what you can do with images and containers. You can start an image with different entry parameters and obtain containers that are slightly different in behavior. I hope that makes sense. And I'm going to also go through a demo in order to make sure it makes sense. The first concept we'll go in depth on is the Docker file. And as I've accustomed you guys, you have the keyword in light blue. The Docker file is a human-readable set of instructions, and let me show you one. And by the way, this model, you can find it on my GitHub account next to the markdown on containers. It will be linked down in the description. You can read it. Don't get scared. All this green text is commented out. It's just instructions for you in case you want to understand more what's happening. But if you're using Visual Studio Code and you download the Docker extension, it will make the text super readable for you. The syntax is as follows. You have a human readable keyword, from, label, run, copy, pretty straightforward. And then you have arguments. Usually a Docker file starts with a from clause because you need a base image, and this is the image of the Ubuntu 20.04 operating system. So what I'm basically telling the Docker file is I want on this operating system to add a few labels, and these labels are straightforward. It's just metadata. It's owner and my name, and the purpose is training. Nothing too fancy about it. And then I want to update the package manager and install curl, straightforward as well. I want to copy the markdown inside of the image at /thecoolestmarkdown.md, also pretty straightforward. And then I'm going to run again the package manager update and installation for the Nginx web server, because I want to show you guys how you can run your own web server locally pretty simply and fast. Then we will expose port 80. As I said here, this instruction doesn't actually expose the port, but it tells the user of the image they should expose port 80. And then we start the main process of the container by running the Nginx server as the main process in the container. Now that we're familiar with our Dockerfile, let's talk about the next step in the lifecycle, and that is the image. Keywords for image are build, pull, and push. Basically, you transform the instructions inside the Dockerfile into a finite project that you can move around. In order to transform our existing Dockerfile into an image, we need one simple command, and that is docker build. The dot stands for current directory because that's where our Dockerfile exists, and -t stands for tag, and I will give my image a name, my training image, and the tag will be latest. Yeah, the version will be latest. And I will hit enter, and this will happen automatically because I have already built this image before, and when you're building the same image multiple times, the Docker engine will use the in-memory information, so you don't have to wait for it that long. Pretty neat feature in my opinion. Now I want to emphasize on something interesting, and you can look at all of these steps here. You will see that each of the instructions in my Dockerfile is a certain step. For example, step 8 out of 9 is expose 80. And then step 9 out of 9 is CMD or command. What I want to say is that your image will be formed from layers, with the from clause being its foundation, and on top of the foundation, each of these keywords will create an additional layer. And I want to emphasize this because in here, for example, we're doing apt-get update and apt-get install, but we're doing them in two different lines, while here we're doing the same apt-get update and apt-get install, but we're doing it in one run command, which means here we will create two layers in our image, while in this example we will only create one layer. And all of these layers, after they're created and added to our image, they get killed as intermediate containers. It's a pretty efficient way to build an image. And now we have this image with the certain ID and the certain human readable name that I gave it. The next logical step for us would be to run our container, and this is the keyword here, or actually the key command in Docker. But yeah, that's what you do with a container. You run it from an image. So let's do just that. To instantiate a container out of our image, we need a simple command, and that is docker run with some arguments. I will give it -d for detached because I don't want my terminal to link to the container. I will also give it -p because if you remember, we are running an Nginx server here, so we need to expose that Nginx server's endpoint to access the web page, and I will do that on host port 8080. So when I do localhost, I'm going to do localhost 8080, and the port of the container is 80. It's right here. It says expose 80, so that should be straightforward. And then I just need to give it my name or my ID. Either or is fine. I will do the ID. Why not? And it will return an ID of its own if it's successful. We can check it's running by doing a docker ps, and yeah, here we have it. Yeah, it's this ID right here. Sorry, this ID right here. That's the name of the image. So it starts with b2ddcc, as you can see. And I didn't give my container a name, so Docker Engine does something funny here. It gives it a random name formed from a human name prefixed by an adjective. So let's access our local host to see that the Nginx server is running. Localhost port 8080, and bam, welcome to Nginx. And this is the Nginx server we are now running inside of our container. And if you want even more proof, because I can do that as well, let's enter the container, and we will do that with docker exec command, -it for interactive and tty, and then I would like to attach to the container's bin bash process. And here we are now root inside of the container. Let's do a list. And if you remember, we asked it to copy the containers markdown inside the coolest markdown.md. Here it is. Yeah, if you want me to show you. Here we go. This is the full markdown that's on GitHub. And for even more proof, we can do curl, because we installed curl right here, on localhost 8080. Sorry, it's port 80. And there we go. We have the same Nginx page running for us. Pretty cool, right? Having put up with me so far, I would like to thank you from the bottom of my heart. I really hope this information was useful to you in case you're trying to understand what containers do and how they achieve what they do. And I hope you realized how easy it is to run an application in isolation on your own host without actually having to install stuff manually. You just write every clause in succession in the Docker file, you build it into an image, and you run it as a container. It's as simple as that. And you can do that for almost anything, as long as it's lightweight. Don't forget about the initial discussion, right? You don't want a huge application inside of your container. You don't want 20 gigabyte of a container, because that's no longer a container. Hey guys, I hope you liked this Docker tutorial, and if you did, please leave a comment below. If you want me to create other tutorials on various technologies, just leave a comment down there. Now, using what we've learned with containers today, we're going to continue our path to DevOps, and we're going to run our 3 applications in containers next time. So, until then, thanks a lot. Have a good day. Cheers.